How does the bond length get measured? Well, I mean, I had this picture of. Access it really quickly. I mean, X-ray diffraction is a very common tool. These are images that you'll see of junctions. This is this is an image from transmission electron microscopy, and so you can estimate the lattice constant and stuff like that from microscopy techniques like this. Okay, and is there any metric that can assist us to identify an effective circuit? That seems to be an upvoted question. Well, I assume you mean not the final answer, right? You mean something that it can tell you beforehand. That's actually a very hard question. And if someone had that ability, that would be very, very effective. But I think the short answer is no. You can have some intuition based on the structure of the trial state, whether that's going to help you get even close to the ground state or not. But in general, there isn't like an easy way to identify, okay, this is going to get me a great answer with low circuit depth and number of parameters. You're asking for the holy grail. Okay. Okay. Let's get back into the final part of the talk. Okay, so putting it all together, there were also questions on can we see like demonstrations of how this works. So let me just take you through an example of how all of this looks like. Right. So this is an example of a 6-qubit Hamiltonian. We don't need to get into the details of what that Hamiltonian is or was, but what this means, and then this was a depth 1 circuit that was used for the trial state, and that meant that there were a total of 30 variational parameters. Okay, all those different theta angles and the single qubit rotations. So that's what you see in this panel here. At every iteration along the optimization, you have all these different theta angles being updated, right? And then you start out at some initial point, and then you have these blue and red points, which basically represent in your SPSA optimization. This is one blue point and this is one red point. Okay, so at every iteration, you're approximating the gradient using just two measurements. There were also questions I saw on choice of optimization. Do they have to be gradient descent? They don't. It can be whatever is your favorite optimizer and whatever works well for the experiment. This is an example of an experimental run where SPSA was particularly useful because you have to deal with stochastic noise arising from finite number of shots and so on. So at every iteration, you have one red, one blue point. You measure a gradient. You approximate a gradient using those measurements and choose a new direction to go in, as I showed a few slides earlier. And finally, you're going to come in and flatten out at some region. It won't go any lower, and that's going to be your final energy estimate. Okay, and then I'll just re-emphasize once again that these are all the different theta angles which are being optimized simultaneously at every iteration. Okay, so this is an example of VQE in action. Let's focus in on specifically the example of hydrogen. Okay, and this is considering just the 1s orbitals. Okay, so for the 2 atoms in the molecule H2, you have 2 1s orbitals, but they're spin degenerate, so that gives you a total of 4 spin orbitals. However, you can identify some symmetries to the Hamiltonian and get rid of 2, and that reduces the problem to just a 2-qubit problem. And then you essentially work with Hamiltonians of this form after some choice of mapping, and I believe this was a parity mapping that was employed for this example. And then you have all these different coefficients. Okay, and this was stuff that Antonio explained yesterday. How these coefficients can be calculated efficiently classically. Okay, and these are basically functions of the interatomic distance, right? So as I go from an equilibrium distance of 0.73 angstrom to 4 angstrom, the Pauli strings are the same, but all that's changed is these coefficients, right? So for every interatomic distance, you have a different Hamiltonian that you have to optimize. So this is also an example of experimental data. This is running it for running the 4 angstrom Hamiltonian here in blue, and then in red this is for the equilibrium Hamiltonian. And each of these is going to converge to some energy, and that's going to be the final energy. I'll just also emphasize here that this Hamiltonian is the electronic Hamiltonian after the Born-Oppenheimer approximation. So this is only giving you the electronic energy. On top of this, you have to add on some fixed nuclear energy that is also efficient to evaluate classically. All right. So then basically by doing this optimization for a bunch of different interatomic spacings, you can generate curves like this. So the red curve, the red dotted line, is basically what the exact energies are, and this is also one of the exercises you have. How do you estimate the exact energy when you're given a Hamiltonian like this? Essentially, all of these are basically Pauli matrices, so you have a matrix representation of the Hamiltonian. You can do an exact diagonalization and find its eigenvalues. The lowest energy eigenvalue is the ground state. So that can be done to generate the red curve, and then these black circles basically represent the experimental data points. What came out from the experiment, and this experiment seemed to have worked quite well. And this is very promising, although it's a very, very simple problem. Now, trying to go to the next step, what happens? Like going from hydrogen just to lithium hydride, okay, which is now a 4-qubit problem. Things, grow pretty quickly in the number of Pauli strings. Okay, what was just 5 Pauli terms or 5 Pauli strings now becomes about 100 Pauli strings, which can mean many more circuits to run with many more post rotations per energy evaluation. In this case, the II, ZI, IZ, ZZ, for the reasons I mentioned before, these all can be grouped into one set. So they only require one set of post rotations, and then the XX is its own set. So you have only 2 sets. And here you can reduce, for the lithium hydride, you can reduce the number of measurements a bit by grouping these 100 terms into 25 sets. Okay, this is for our chosen representation in a 4-qubit problem. Okay, and with that, you can then try and run the optimization for lithium hydride as well. And there's a lot going on here. So let me walk through this very, very slowly. Okay. So on the left is the example of hydrogen, and this was an experiment run back then on a 7-qubit device. Okay, so if you can connect this back to what I was talking about, how do you choose if you have a subset to run? How do you choose which pair do you choose for the experiment or for your hardware run? You basically look at all the information you have about the circuit about the quality of the coherence times and the gate errors and so on. Okay, so the hydrogen example, as we saw, worked quite well. The lithium hydride, seems to deviate quite a lot from this dotted line, which is what the correct answer should be. All right, and particularly interesting are points like this. Points, this point here, pretty big error. That bump is pretty interesting right there. Okay, and this comes back to this question: what's the point of running any of this? Why not just wait for fault tolerance? It's because this gives you deep insights into what is limiting us. Understanding the source of error when you're addressing this very standard problem with a completely brand new paradigm of computing is very instructive. So these are 2-qubit, 4-qubit, 6-qubit Hamiltonians. These are matrices that one can trivially diagonalize on a laptop, right? Knowing the answer is very easy for these problems. And the point of running these on noisy quantum devices is to understand better what are the limitations. All right. So what you see in these shaded circles here, these are basically simulations of the noisy experiment. So this is also something you can do in Qiskit, where you have access to noise simulators. Okay, you have different models you can include, such as models that account for T1 and T2 errors and so on. Okay, so one thing you can see from these numerical simulations is okay. So by the way, the color density plots represent a histogram of outcomes from 100 different simulation runs. So the blue was just one experiment on hardware. Sorry, the black circle was just one experiment on hardware, and then all of these different shaded regions represent 100 different numerical simulations of the noisy experiment. Okay, so and it captures some of the features quite well. It captures this difference here. It captures this bump between 2 and 3 angstrom, and so we can really begin to identify what are some of the limitations. Okay, and you can see that even in simulation, you also have this this almost a spread in results. So which means that the classical optimization isn't getting you to the same point even in simulation every time. It can take you to different points. So in fact, if you see the curve on the right, you have almost a bimodal distribution. You have something here, and you have something peaked around there, and you also have a distribution of results there, right? And the top distribution is clearly worse than the bottom, but it basically is indicative that your classical optimization is getting stuck in a local minima. Okay, so this is stuff you can see. All right, and then another nice thing to kind of also focus in on is even the simulations of the noisy experiment. They seem to have this offset almost, right, from the dotted line. I mean, the hardware experiment itself has its errors, but even the simulations have this offset, and this is also a consequence of decoherence of T1 and T2 errors. And these are all kinds of things that I strongly encourage you to play with. The tools are all there in Qiskit to simulate different noise models and see how different strengths of noise affect the accuracy of these kinds of computations. Connecting back to the question on how much circuit depth is enough, right? So one big reason for why this point is so far off is at that point you actually need much more circuit depth in your hardware efficient trial state to be able to access this energy. So what all of these different experiments used were only depth 1. So this was only one entangling block. So you needed more entangling blocks. Okay, and this raises the question then, well, why didn't we go for more entangling blocks? Why didn't we go for more circuit depth? Right? And this is a slightly researchy slide, but I hope I can walk you through this as well. This basically is showing you the error in energy, okay, as a function of noise strength. Okay, so assume that the noise was very low. If the noise was very low, you could basically keep increasing your circuit depth, very nicely, and then you could get extremely low errors, in lower than 10 to the minus 4. And this is by entanglers 8. This basically means a depth of 8. Okay, so when the noise is extremely weak, you can go to much longer circuit depths and have better approximations to the ground state. However, when the noise is very large, you don't have the benefit of going to long circuit depth, right? The long circuit depth is actually worse than a trivial circuit depth, right? And this is the interplay. To be able to benefit from more circuit depth, you need your noise to be much smaller. But if your noise is very large, you're better off operating at limited circuit depth. Okay, so understanding all of this is an extremely important game in this era of noisy quantum devices. All right. Okay, maybe I can pause and see if there are any questions related to what we've discussed so far.
Yeah, Abhinav, can you hear me now? All right, that's right. Good idea.
So I see a question on how is lithium hydride a 4-qubit problem. That's a good question. So you have the 1s for the hydrogen, and then you have 1s and 2s and 2p orbitals for lithium, and you also have a plethora of higher orbitals. But you can basically restrict yourself to how far you want to go, and another way that I briefly mentioned on how you want to reduce the number of qubits. So first you can reduce, say, 2 qubits based on some symmetries in the Hamiltonian, and then after that you can freeze in some of the core orbitals. So for instance, the 1s of the lithium, because that isn't very strongly interacting with the other orbitals, and this is an approximation. But for simplicity, we've made use of freezing of core orbitals and then making use of some symmetries to reduce that problem to one with just 4 qubits.
Awesome, thank you. Abhinav, are you able to hear me now?
How can we measure the Pauli strings in groups in IBM machines? Does that mean we perform gate operations not after measurements? You measure those operations after the state preparation. Okay, so I can. So if this was the circuit that you use for the state preparation, you then have a layer of post rotations that you have to apply, depending on what that Pauli string is. Okay, what defines number of qubits required to simulate any molecule? Yeah, that's an excellent question. I think I briefly mentioned this. So it relates to the number of orbitals that you consider in that molecule, in the molecular simulation. Okay, so in general, if you had n spin orbitals, you would need n qubits. Right? So So in the case of the hydrogen, for instance, we considered 4 spin orbitals, and in general that would mean 4 qubits. But then you can get rid of at least 2 by identifying some properties of the Hamiltonian. But then you can also make more approximations, like what I was referring to as freezing of core shell electronic orbitals and so on. How many qubits are required to simulate lithium sulfide? This is a promising material for systems of battery. Yes, there is actually some work that you can find on the archive, and which you might find interesting. Once again, it really depends on the number of orbitals that you want to consider, and the amount of approximation you make there. Okay. Yes, the lithium hydride bump is indicative that the state that you prepared with that limited circuit depth is not capturing all aspects of that ground state, of the exact ground state. Okay, I think that's hopefully good for now. Let me talk about the final part of my talk, which I will start with a short story, okay, of the longitude problem. And perhaps many of you aren't familiar with this, but this was one of the most iconic engineering problems of the 18th century, which was basically all of business was through ships or big business, and trade. And these ships needed to know where they were. They needed to know their geographic location based on longitude and latitude. So longitudes are the lines that run from the North Pole to the South Pole, right? And the way they did that was they would have a reference clock. So say they were leaving England, these ships, they had a clock that was timed to England time. And then when they were at sea, they would figure out what the local noon time was from, say, the position of the sun, and then compare that to the reference time they had, when they left shore from England. And using that time difference, they would try and evaluate what the longitude was. Okay, and this was extremely important because all these reference clocks failed. And why was that? Because they were, big mechanical objects like what you have in this figure, which were extremely sensitive to perturbations from the environment. Okay, they were sensitive to changes in humidity, changes in the rocking of the ship, changes in temperature, and so on. And this was a big challenge because the imprecise knowledge of the longitude led to shipwrecks, failed business, and so on. And this was a huge problem with a great amount of prize money even back in the day. So this was the first iteration of this clock that this great inventor Harrison made in 1730, and you can see it has a whole bunch of different mechanical moving parts, and there are actually some funny solutions that people tried to come up with that included barking dogs. Look this up if you're ever interested. But so he worked through many different iterations over a few decades. This was his second iteration, and then his third iteration. And in this third iteration, the Harrison 3, he actually came up with a device that would offer robustness against temperature fluctuations. Okay, and that basically led to the invention of the bimetallic strip. So the pursuit of this big, large problem, the longitude problem, led to other technologies. Okay, and finally, by understanding all the different error mechanisms that are affecting the performance of this clock that can work at sea, he finally came up with this pocket clock. Okay, the marine chronometer. Okay, and this was hugely transformational, and this was really a journey that over many decades that finally turned out because of an understanding of the many different errors and figuring out methods to fix them. Okay, and I find that the story really connects quite well to what we're doing with quantum computing, okay, today. And I must credit this to Professor Simon Benjamin from Oxford, and I've kind of heard of the story down the grapevine. But the analogy works really well of trying to understand errors on noisy devices, and maybe then coming up with tricks to try and fix them. Okay. For that, let me get into the final part of my talk. That's error mitigation. Okay, and the idea here is basically that we saw that these different expectation values, like the energy, for instance, is affected by noise. It's affected by, say, our T1 and T2, and so we can represent that noise by some parameter lambda. Okay, and for a reasonably small noise parameter lambda, you can essentially express this expectation value as a linear as a Taylor series in lambda around its zero noise limit. Okay, so we're going to call this the zero noise limit. And the question we're asking is, you have a noisy device using noisy measurements. Is it possible for us to extract what the result would have been in the absence of noise? Okay, I mean, in the context of our regular day-to-day devices, this isn't a completely unfamiliar context, right? Concept. I mean, noise-canceling headphones, for instance, make use of noise in a slightly different way. But the idea that one could use noise to nullify its effect is not that alien an idea, right? Specifically in this context, assume that I had, as an experimentalist, I had the ability to control my T1 and T2 precisely. So what was 100 microseconds, I've been able to make it 50 microseconds, right? So that means, for instance, I've been able to scale the strength of the noise by some factor C. Okay. So here, expressing this only to second order in lambda, you have this E star term, which is the noise-free term, which is what we want to access. And then you have this linear term in lambda, and then you have higher order terms. When you amplify the noise strength by a factor of C, you once again have this E star. Now you've gotten this C lambda here, and then again you have higher order terms. Now by combining these two noisy measurements, okay, using a linear extrapolation like this, what you can see is that you now have an estimate where the leading order noise term is order lambda squared. Okay, so by two wrongs, you've been able to make something that's more right. Okay, you've been able to have a closer access to E star. And in general, this idea is called Richardson extrapolation or zero noise extrapolation. With n noisy measurements, you can suppress the highest order noise term to order lambda to the n. Okay. The question though is, how do you accurately scale the strength of the noise? Okay, this is not a trivial task. You can't go up to you can't open up Qiskit or go up to the quantum experience and say, let me change the T1 and T2 times. That's not possible. So you can play one more trick there. If you had something like pulse level control, okay? So say you had a 100 nanosecond or a 10 nanosecond pi pulse, okay? And say that's represented by this, okay? Assuming that the noise does not change over time, let's stretch that out, that same pi pulse, to a 20 nanosecond pi pulse, okay? And not only for just that pulse, for every other pulse in your circuit, let's stretch that by that factor. Okay, then the result, the expectation value, the mean value that you measure after this circuit is going to have a noise that's 2x amplified. Okay, so basically what I showed on the previous slide, you have one noisy estimate, you amplify the noise, it gets even worse, and you can extrapolate down to what that noise would have been, what the expectation would have been in the absence of noise. Okay, to some order. Right? So this can be a very powerful technique to extract meaningful computations even from noisy hardware. Right. So this is a really nice visualization of experimental data, by the way. Okay, this is experimental data where you try and operate a trajectory. You try and operate a circuit that takes your qubit along a trajectory along the surface of the Bloch sphere, from the ground state to the excited state, right? And you want this to be along the Bloch sphere, but because of noise, this doesn't quite get up to the one. Okay, and you also see it compressed towards the center. That's also because of noise. Now, if you amplify the noise by a factor of 2, okay, which is what I'm doing here, then you can see that you're even further away. You only get about midway with this experiment. But by combining the red and the green, you can generate what the trajectory would have been in the absence of noise. And this now maps beautifully what the trajectory would have been. that's going right along the Bloch sphere, approaching the 1. Okay, so this is an example of error mitigation on 1 qubit. But then you can also then revisit some of the problems I spoke about before our short break, right? The lithium hydride simulation, for instance. What was preventing us from going to larger depth? It was that we were affected by the effect of noise on the circuit, right? But now we seem to have a trick up our sleeve that can nullify the effect of this noise to some extent, right? So that lets us go to a much longer circuit depth. Okay, so these represent the raw experimental points, which are measured at 4 different noise factors. Okay, and if you compare these to this, these raw points are actually even worse. Why are they worse? Because the depth of the circuit is longer. Okay, but because you have these additional noisy measurements, you're able to extrapolate down to what the result would have been in the absence of noise. Okay, and now you see these white curves line up much better with the green exact energies. So this is an important flavor of techniques and experiments that can be useful for performing computations on even noisy hardware. Okay, I'll just emphasize that these are really only benefiting mean values, expectation values. This isn't something you can do for single-shot measurements, which are relevant for some other algorithms like phase estimation that you might have learned in the past. But for problems like this, where you rely on expectation values, and this is not a small set of problems that people are interested in. You might be interested in simulating energies of molecular systems, of systems in condensed matter physics. You might be interested in simulating the magnetization of some complex frustrated magnet. All of these are examples of problems that rely on expectation values. In machine learning, people talk of kernel methods. That also translates into an expectation value. So there are a whole class of problems that can benefit from techniques like this. Okay. So with that, let me just finally summarize over what we've covered today. I started out with a brief hardware recap, and then discussed what kinds of noise one has to deal with in our hardware. And the motivation behind this was to connect this to the performance of algorithms that are geared towards noisy hardware, like the variational quantum eigensolver. And we looked at this in great detail in the context of the lithium hydride, in the context of molecular simulation, lithium hydride being one example. And then we saw how noise on the hardware affects the performance of the molecular simulation. In practice, you have these very large errors, but understanding those errors is an important stepping stone in the long road to fault tolerance and error correction. But in the meantime, this whole approach can help us devise techniques and tricks like zero noise extrapolation, which can enable access to accurate computations, certain accurate computations, even on noisy devices. Okay, and over the last 2 days, while a lot of this has been focused on chemistry, the techniques in general have very wide applicability. You can address problems in nuclear physics, in condensed matter physics, magnetism, even beyond quantum simulation. Problems in machine learning and finance and so on. It really starts out with having to map out that problem onto qubits. So once you have a qubit Hamiltonian, you can play this whole game of trying to find its ground state energy using this variational approach. Okay. With that, I think I want to thank you for your attention. I hope this was useful for all of you, and I hope this also motivates you to try and run experiments on the hardware, run experiments with noise simulators, get a sense of the limitations, try and develop tricks to kind of mitigate the effect of these errors, and just develop a general intuition for what it takes to run experiments on actual hardware. Okay.